stationary box. All right, there it goes. Stationary box. So we have a box. Right, and that box has mass M1, right? And that box is on a surface. Okay. And M1 has mass of 10 kilograms. 10 kilograms, right? And okay, and so now we're gonna say that this box is stationary, right? So the box is not moving, right? So we got M1 10 kilograms, and we're gonna have mu of S, and mu of S stands for what? What's the S stand for? We're gonna call that, we're gonna get at a value of 0.6. That's our mu of S, all right? And so now, question is, I'm still waiting for somebody to tell me what mu of S is. All right. But the question here is calculate and then we'll have an applied force. So let's do this. Let's put an applied force. Applied force of 5 newtons, right? So I think that's all we need, right? So now I'm asking you for help. How do we solve this problem? We want to calculate, let's see. We want to calculate the calculate the well, we might have a number of things we calculate, but let's start with the normal force. Let's calculate the normal force. Okay, that's the first thing. Calculate the normal force. Okay, so how do we do the free body diagram? That's a question. What's the first step in the free body diagram? Forces. Yes. Identify the forces. Yes, sir. Okay. So what's the forces acting on the box? Gravity always. Gravity acts on everything all the time. And that's equal to what? mg. What else? Yes, right? So if we apply the force this way, right, then our static friction is going to point in which direction? We applied the force that way. So which way should the opposite of which motion we expect? Right? So static friction works against our motion, just like kinetic friction. Static friction is just the friction that you experience before you start moving. That's static friction. That's what we're dealing with now, right? F, let's say of S, and then we're gonna have mu of S, and then F of N, right? That's the equation. What other force do we have? Normal force. Yes, indeed. Normal force. Normal force. And that acts perpendicular to the surface on which our object moves. So now what? What do we do now? What's the next step in the free body diagram?
Add all the forces together.
Sum all of the forces in each direction. Right? So what are the forces in the x direction? And we're going to say this way is positive. Going to the right is positive. Going to the left is negative. And obviously going up is positive and going down is negative. Right? So now what? Got to sum the forces, right? So which one I write first? Huh? The positive one, yes. But which one is it? No, we're guessing, right? Which one points? Well, actually, okay. Actually, let's do this. It should be the other way around, right? I did that wrong. All right. So it should be, this is positive, and this is negative. Sorry. Okay. Or we would have had to put the applied force on the other side. So let's go with this, right? So going this way is positive. So we write the applied force first, right? Minus what? Static friction. And that equals to what? It's a stationary box. Zero. And what about the y?
The normal force minus gravity.
Yep. Normal force minus the gravity equals 0. So now we have two relationships, right? We got what? Therefore, and we can write one thing for both. Therefore, right? F of A is equal to what? F of S. And F of N is equal to what? F of G. right? And so let's say this. Let's do this then. Right, so let's answer this question first. Okay, calculate the normal force. Right, the normal force is right here, right? We got that from our free body diagram. That's the normal force. And the normal force is equal to the weight. And the weight is equal to what? M times G. Right? Which would be what? 10 kg times 9.8 meters per second squared. Which is going to give us 98 newtons. So that would be the normal force. Right? And so we could take this out. Right? Now let's say we're gonna calculate. So we don't need, all we needed from the very beginning was what? The mass of the box and the applied force. 10. Right? So now we got what F of n is equal to. Now we can come here and we can calculate coefficient of static friction. That's the second question. And so, if we notice that our static friction is right here, right? And we know the equation for static friction is right here, right? Get that out, my red marker. There we go. Get that out of there. All right. So what we're gonna do? We're gonna say, all right. Well, we need to calculate the coefficient of static friction. That's inside of this equation, right? So we know that F of A is equal to what? Huh? 5 newtons. Right? We said that. That equals 5 newtons. And F of A also is equal to F of S. So F of S is equal to 5 newtons. Right? So then I'm going to take my equation there. F of S at the top equals what? Mu of S times F of N, right? And I know that what? F of S is equal to what? 5 newtons. F of N is equal to what? F of N, 98 newtons, right? 98 newtons. So my coefficient of static friction is what? 5 newtons divided by 98. Which I don't know what that number is, but I know it's less than 1. And that's the requirement for the coefficient of static friction. It's less than 1. Greater than 0, but less than 1. So what did we do? We calculated the normal force and we calculated the coefficient of static friction. And all we knew was what? The applied force and the weight of the box. Okay? So understand, we don't always have to calculate acceleration. There's other things we can calculate besides acceleration, especially if the box is stationary, right? There's no acceleration. So we're not going to calculate acceleration on a stationary box. That makes sense, right? But on a non-stationary box, we will. Okay. And let's see. So now let's take the same. Oh, did we get a number for this? 5 divided by 98? 0.051. Okay. That's a really low static friction, but it's like ice or something. 0.0 what? 51. That would be the coefficient of static friction. Okay? But that's on the stationary box, right? Obviously, a stationary box doesn't have an acceleration, so we wouldn't calculate the acceleration on a stationary box. So on a stationary box, we would be looking at things like the normal force or the coefficient of friction. All right? See, these are things you can remember, right? If you get organized and, I mean, like I say, I've been doing this a long time, so I kind of benefit from just years of experience, but it's certain things you can see right away, right? Certain things you know that shouldn't happen. Like I'm saying, right? When you see stationary boxing, you know I'm not going to ask you to calculate a what? Acceleration. It doesn't make sense. Okay? So now let's look at the non-stationary box. All right, so we're pretty much gonna be the same, right? But what we're gonna do, we're gonna change the title, obviously, to non-stationary. And then we're gonna add a larger applied force, because I think 5 newtons is probably too small to move a 10 kilogram box. I just know that from experience, from doing this over and over again. All right, but if we put 50 newtons applied force, that box is gonna move. So let's change our applied force to 50 instead of 5. And because we know that it's a non-stationary box, then our friction turns into what kind of friction? Kinetic. Kinetic. Good. All right, non-stationary box. And we're gonna change that to kinetic. Let's take this out. Non-stationary box. Non-stationary box. All right. And now, we said our friction, which works against our applied force, which is 50 newtons, is kinetic now because we're moving. So F of K equals mu of K, F of N. And we still have the same convention. Down is negative, up is positive, to the left is positive, and to the right is negative. So now this is the non-stationary box. All right. Remember, we got 4 situations. We got stationary, non-stationary, box on the inclined plane. and the Atwood machine. All right. So this video is covering the first two. We already got a video on the Atwood machine, right? So all there is left is the box on the inclined plane. I think we got a video of that one too. All right. So help me out. Now listen. What's the steps? What we doing? We've already identified the forces, right? We already did that, so what's the next step? Sum all the forces. Sum all forces in X, sum all forces in Y. Okay? What are the forces in the X? Okay, and which one I'm writing first? The applied force minus the friction force. And that equals what? Huh? Mass times acceleration. Because we have a what? Acceleration. Right? This is a non-stationary box, so we're going to say the acceleration is this way. It's accelerating that way. It's non-stationary. It's going that way. And what about Y?
The normal minus the gravity.
Yeah, the normal force minus the gravity. And that equals what? 0. So now we see how now we should automatically notice what's the difference between the two situations. Yeah, we know that one is accelerating, one is not. But I'm talking about in terms of the equations. Well, in the first situation, both are 0. In this situation, only one is 0, and that's for the Y, because the box is not moving in this direction. It's only moving like that. So that's what we should notice right there, right? Is that when I'm talking about a non-stationary box, I should have one equation equals 0, one equation MA. Because I know I'm accelerating now. In the stationary box, I wasn't moving in the X direction or the Y direction. So both of these equal to 0. Okay? All right. So here. All right. So let's see. So here we're not going to calculate the normal force. What we're going to calculate first is the acceleration. Let's do that. Calculate the acceleration here. All right, so calculate the acceleration. I need a red. Calculate the acceleration. Yeah. All right. So immediately we notice that what? We got acceleration right here. Right there. Right? So then it's easy, right? At least it looks easy to start with, right? So we got A And so all we gotta do to get A by itself on this side is to do what? Divide both sides by M. So when I do that, I'm gonna have what? F of A minus F of K, all of that over M. Right? And I know F of A is equal to what? 50 newtons. Right? Minus what? Mu of K times F of N. And that's all over what? 10 kgs, right? So on this one, right, it is a requirement. In order for you to calculate the acceleration, we must know this value. So that's another note. That's another difference you can pick up right away. If I give you the coefficient of friction, then I'm normally either talking about the non-stationary box. Well, if I give you the coefficient of kinetic friction, then you know it can't be the stationary box. We're talking about kinetic friction. We're talking about things that are moving. Okay? So let's just make this, let's make that correction. And I'll say mu of K is equal to 0.4. Okay? Because we're going to need that in order to finish this calculation. So I'm just making this up, y'all, on top of my head. All right. So if we got 0.4, and so now we had to, so now we can replace it right here, right? So we have what? 50 newtons minus what? Mu of K, which is 0.4. Now we need F of N. That's all we need now to calculate the acceleration. And where do we get F of N from? F of N is equal to what?
F of G.
F of G. Yes, sir. All right? So, all right, we can write it off to the side that what? Therefore, because of that equation, what? F of N is equal to F of G, and F of G is equal to what? M times G. And we're going to what? That's what? 10 kilograms times what? 9.8 meters per second squared, 98 newtons. So now I just plug that in, right? 50 newtons, 0.4 of 98 newtons. So that's pretty much half of 98. What's half of 98? 49. Yep. So that's going to be just enough to do what? Make the box move. Look at y'all, see what I'm saying? Do y'all see what I'm saying? Do y'all follow what I'm saying? Look at what I just did. I said it's 50 newtons right there. That is the applied force. So what opposes the applied force? The friction. The friction is what? 0.4 of 98 newtons. So what's 0.4 of 98 newtons? That's a little less than half.
39.2.
39. So let's replace it. Now look at what happened. Now you tell me math doesn't make sense. Math is just a bunch of numbers and stuff, and it's not making sense. So look, if I apply 50 newtons, and now I'm at what? Minus what? 39 newtons for the friction, right? What if that was 35 newtons? What would have happened? What if my applied force was 35 newtons?
The box would have moved.
Yes. Yes. Because it wouldn't be enough to overcome what?
The friction.
Friction. Yes. So you have to make math make sense to you. You can't just do math and then get a number and say, oh, okay, that's it. We done. No, it has to make sense to you. So if I didn't put but 35 newtons on the box, it wouldn't move. According to this coefficient of kinetic friction, which is defined by the surface you're trying to move the box across. All right, so that would be what? 50 minus 39 over what? 10 kgs. That's what, 11 newtons? That's 11 newtons divided by 10 kg, right? And that's gonna give us what? 11 divided by 10, what is it? 1.1. That sounds like a great acceleration. All right, and newtons divided by kgs is meters per second squared. Just trust me on that. You don't have to go through the math. But that sounds like a reasonable acceleration for a box across a surface. 1.1 meters per second squared. Yes, indeed. All right. So let's make sure we're getting all this on camera. Oh yeah, it's all left. It's all left for you to see. Move that down a little bit like that. Maybe a little over. I need something that move on its own. Y'all young, y'all know better than I do. What can I get? Huh? Don't they have something that do that with the cell phones now to make content? Don't they have that now? I be seeing commercials about that. Where the guy said you can make your content by yourself and you walk around and the cell phone follows you and stuff. You seen that? Yeah, what is that called? You know? All right. What is it? The Oswald? An Osmo. That's like oh, it's a camera. Oh well, that's gonna be expensive. I'm talking about something where you could just put your phone on it and then your phone follow you. Yeah. I don't want to buy a whole nother camera. No, indeed. But that's how it was set up in James Hall before they tore it down. Yep. The camera would follow you through the class. It wasn't good though. I tell you, still wasn't good. This is much better. But you don't. I can't get out everything in the image though, because the camera don't move. All right. What time is it? 2:11. Okay. All right. Like I said, I think I got the Atwood machine already recorded. That's on the canvas. So the only other situation is the box on the inclined plane. So let's do that, and we'll be done. Box on the inclined plane now. Box on an inclined plane. All right, so we got the inclined plane. All right. We got a box on that inclined plane. Okay. And we call that M1. All right. So, so what are the forces? So identify, that's the first step, right? We identify our forces. What are they? Friction force. All right. Actually, there's two situations here, right? There's what? the box sliding down, and then the box doing what? Going up. We got two situations here, so actually that's 5, right? Stationary box, non-stationary box, box down the incline plane, box up the incline plane, and the Atwood machine. All right, so in this situation, we don't have an applied force. We don't need one, right? Because we're on the inclined plane, we don't need an applied force for the box to do what? Slide down. We need an applied force for the box to do what? Go up, though. But to slide down, we don't need an applied force. Gravity will do that for us. All right? So let's identify. So what this force acts as what? This is what? F of G, right? F of G, the gravity. Gravity always acts straight down towards the earth, no matter if you're on the inclined plane or not. It acts straight down. Now what we're gonna use is the what? Projections of the gravity. Like we did with the vectors, right? That's why we learned the vectors first. Okay? And so this force is called what? This force is perpendicular to the surface. We call that what force? Normal force. Okay? And of course, we know that the box is going to be doing what? Accelerating which direction? Down the inclined plane. Because of gravity. So, in that case, then that we know that what? The force that works against the box sliding down the inclined plane is what? Friction. We'll put it right here, and we'll call it F of K. All right? So again, after we have identified all of the forces, what's the next step? Sum. Sum all of the forces up. X, sum, F, Y. Gotta make sure we've identified and covered all of our forces too. Right? And we keep in mind that since we're on the inclined plane, our Cartesian coordinate system is tilted. This is X, this is Y. All right, so when we sum our forces in the X, what are they? Well, when we take the projections of our gravity, which is what we're going to do, that's the green, right? So because we know, remember what I told you about these two angles? Well, let's take the projections first. We're going to take the projections of this vector, right? The X and Y projections, right? That ain't look good. Do that, man. All right, so this is like the hypotenuse of a triangle. This, the actual vector. And then we're gonna make a triangle. There we go. See that? So what that means is what? That means that, and we said that this angle right here, is called theta, and it's the same angle right here. These two angles are the same. So whatever they tell you is the angle for the inclined plane, that's going to be this angle right here. But we have to take the projections, right? So how do we take the projections? This is going to be the adjacent side to this angle. So this is what? Cosine. So it'd be what? FG cosine theta. This is the opposite side to that angle, so that's going to be the sine. FG sine theta. Right? So now we can clearly see in the x direction we have two forces. What are they? No, acceleration. Friction is one of them. Acceleration is the result of a force. Okay? But we got friction and what else? Sometimes it's, if we, you know, when you first start doing this, you might not, sometimes you just forget about it, right? But it's this one. This projection is pointing in this direction, right? Because gravity works to do what? Pull the box down the plane. So this projection of that, this is gravity. So the projection of that gravity is this, right? So you can actually put an arrow at the end of here. So that projection is what actually opposes the friction. Y'all following me on that? Y'all look kind of lost.
Like basically, the gravity is pulling it down. It always pulls stuff down.
Right, but it can't pull it through the inclined plane. It's not going to pull it through the inclined plane, but it's going to slide down. But that's gravity making it slide down. Following what I'm saying? Right? And so when we do these tug of wars, right, the forces have to be on the same plane. This force here, gravity, nothing is on that plane. Y'all see that, what I'm saying? That's why we took the projections. When we take the projection, this force, this projection here opposes this force. This projection here opposes this force. This one opposes nothing because gravity works straight down. Gravity doesn't work on an inclined plane. It just works straight down no matter what happens. So we have to take the projections to actually make this make sense. There we go. So if we coming down, the plane is this way is what? Positive. Going up is negative. Right? So then we're going to say what? FG sine theta minus what? FK. And that equals to what? MA. Yes, indeed. Now what about the Y? Do the same thing on the Y. This is up is positive, down is negative. So what forces act like this?
The normal force in the FG.
Which one I'm writing first? FN. FG cosine theta. And that equals what? Huh? Don't guess it. There's nothing to guess. Remember, there's a question you have to ask yourself. There's only two situations. Does the object move in that direction or not? Does the object move in the Y direction? No.
So it's 0.
So it's 0. Okay. And so this is another one where I'll be more than likely I can ask you to calculate acceleration, right? So that'll be a sort of a question here, right? Calculate the acceleration down the box, down the inclined plane, right? Acceleration of the box down the inclined plane. Again, it's real simple. We just come here and just work with the equation with the acceleration in it. That's where we start. A is equal to FG sine theta minus F of K, all over M. That's it. So now we gotta fill things in accordingly, right? All right, so FG sine theta, and this is mu of K, and of course we're gonna need, that's gonna be given to you in the problem, the mu of K is gonna be 0.4 again, all right? And so we can replace F of K. We know the equation for F of K is mu of K, F of N. So we can replace that right here. Mu of K, F of N, all over M. Right? And we can go further. And now we can say what? F of G sine theta minus mu of K. And we know F of N is equal to, right? F of N is equal to what? F of G cosine theta. F of G cosine theta. So we replace that F of N right there. The F of G cosine theta. All of that over M. And now we have a common term, so we can factor that term out, F of G, open parentheses, sine theta, minus mu of K, cosine theta, close parentheses, all of that over M. And that's the final answer. And so you would just, now you can come in and just do, and of course you would know what your incline, you would know what your theta is too. What's the incline plane? 45 degrees. And so here, now you have everything. You have M, 10 kilograms, you have your theta, 45 degrees, and you have your coefficient of kinetic friction. And of course, FG is just what? Huh?
9.8.
No. FG is M times G. Right? So then that means this can cancel. These two will cancel anyway. So your final answer would be this. It would be G times, and I think that's what we got in class the other day, right? This kind of looks like similar to what we got in class. Cosine theta. Right? So again, so the acceleration of the box down the inclined plane would depend on gravity, of course, the angle of inclination, and the coefficient of friction. Anybody got a number? Did anybody calculate the number? No? Alright, so tomorrow we on chapter 5, y'all. We chapter 5 tomorrow. Yeah, so I think like I said, I think I recorded the Atwood machine and the box on the inclined plane going up the inclined plane. So those are already on canvas. So once I put this on here, then you'll have all situations, videos for all situations. All right, I think we're gonna wrap it here. About 3 o'clock now. What time is it? 2:30. That's good. Any questions, concerns, or comments? No? Alright, and just so before y'all go, I'll write them here. And we'll put them on the recording too. Let's write them down so we don't have no confusion about what is to be expected for chapter 4. Let's just turn the camera. There we go. So 1, stationary box. 2, non-stationary box. 3, box, down, and incline plane. Box, up, and incline plane. And the Atwood machine. The Atwood machine. Five situations. All right, y'all. I got no questions. I'll see y'all later.